All right, Andrew. Good times, great oldies. Have I already talked about continuity this year?
Yes.
Yes, I did. You remember what the definition of continuity is, Andrew?
Continuation.
It is a continuation. So, Andrew, here we go. Mr. Baker already wrote this on the board once this year, and I'm writing it again. This is the definition of continuity, okay? We broke this down in class just the other day, and I said, you know, really, this expression on the left-hand side is that you're really approaching, you know, the limit as you approach C from the what? The left.
And the right.
And the right, Andrew, right?
Yeah.
So, Andrew, like back in your notes, I said, holy cow. When you see the word continuity, the buzzword continuity, continuous, continuity, continuous, what does the AP exam really love for you to do? They want you to talk about the limit as we approach C from the left. They want you to talk about the limit as you approach C from the right. And they also want you to verify that it equals f of C. Now, why is that last part so important? Well, because again, Andrew, I've drawn this graph on the board once already. We'll do it again. You know what I'm saying? Mm-hmm. So, Andrew, let's say I had a graph that looks like this, right? If I said, what's the limit as I approach C from the left and approach C from the right, what would the limit be for?
Yes.
Well, by golly, the left and the right equal each other. Mr. Baker, it's continuous. No. Okay? You have to verify that it also equals f of C. F of C in this case is like 2. So is that function continuous? No. Continuous means no holes, no jumps, no gaps, no breaks, nothing, right? It has to be a smooth curve, right? So, Mr. Baker, you know, BC kids, they're taking a 2-day test. They're finishing up today. You know what I'm saying? What's continuity on their test, on their FRQs? Yeah. Did everybody remember it? Did everybody remember to check this last part right here? No. So, Andrew, here's my forewarning. Do you think you're going to have this on your quiz on Monday?
Yes.
Do you think you need to check the left, the right, and the function value?
Yep.
Am I going to get 100% on Monday?
Probably
Why not, Andrew?
Because people aren't going to study.
Colin, you're going to study, aren't you?
Yes, sir.
Good. All right. So here we go. Now, Andrew, if I picked up that dot though, and like plugged it right in there, you know what I'm saying?
Yeah.
That graph's continuous. There's no holes, jumps, or gaps. We're good to go. Okay. All right, let's have some fun. A few examples here. They love piecewise functions. Okay? All right. Question is going to say, is this function continuous at x equals 2? Question mark. Okay? Is this function continuous at x equals 2? All right? What should come to mind, Andrew, when you see the word continuous?
Continuity.
Andrew! Just, you can use layman terms, I don't care. The left, the right.
Is equal to f of c.
The function, okay.
Yeah, the function is, yeah.
All right, Andrew, let's just, this is why we're practicing. All right, so Andrew, I see the word continuous. The limit from the left has to equal the limit from the right, has to equal that function value, right?
Yep.
If that always comes to your mind, you'll never miss a problem.
Right.
Okay? So, Andrew, limit as we approach 2 from the left. Which one of these is the left one? When you're less than 2 or when you're greater than 2?
Less than 2.
Yeah, when you're less than 2, you're coming in from the left. So, proper notation, you would put 3x squared plus 2 in here, right? You would plug in 2, you get 4, 12, 12 plus 2, you get 14. You're like, okay, that's cool. You do the limit from the right, right? You got negative 2x plus 16. You plug in 2, you get negative 4, and you get 12. You could stop right there, Andrew. Because what just happened? The limit from the left did not equal the limit from the right. You could just stop, right? So is this function continuous at x equals 2? No, right? Because again, if you wanted to, really got to practice start writing this stuff. You really got to start practicing with this stuff right here. Andrew, the limit from the left, right,
Mm-hmm.
did not equal the limit from the right. You know what I'm saying?
Mm-hmm.
Just practicing that notation. They love that on the AP exam. You know what I'm saying? When else do you write this kind of phrase when the limits don't equal each other from the left and the right? You had it on your quiz.
Oh, when there's like
When the limit does
Not
not exist, right? Yeah, that's good. That's good notation to use. All right, Angela, let's do another one. Part B. Oh, let's call it example 2. I'll call it example 2. All right. Same kind of question here, Andrew. Is that function continuous at x equals 2, right? Is this function continuous at x equals 2? Question mark. Andrew, what comes to mind when you see the word continuous?
the limit from the left and the right. They have to equal each other and equal FC.
Go team. All right, Andrew, let's do it. You ready?
Yep.
Which one up here is the limit from the left? The
Is
top function or the bottom one?
top.
The top one, right? So if I'm coming from the left, I would have the sign of pi x minus 1. What do you get, Andrew, when you plug in 2? Sine of 2 pi? What's sine of 2 pi?
It's 0.
It is 0. 0 minus 1? Negative 1, right? What would be the limit as we approach 2 from the right side, Andrew?
It would be
Like if I plugged in 2.
-1.
Yeah, because the cosine of pi, the 2's would cancel, so you're really just doing the cosine of pi. What's cosine of pi? Oh, it's negative 1. Andrew, is the function continuous?
We don't know yet.
Thank you. That's good. We don't know yet. Okay, we don't know yet because do we need to write something about this, Andrew, somewhere on our paper?
Yes.
We do, right? What is f of 2? Well, you've already done it, which is nice. If I wanted to say what's f of 2, I would have to plug 2 into one of these functions. And technically it's the top one, right?
Mm-hmm.
Because you're less than or equal to 2 right there.
Right.
So you plug 2 in there, but you already know what you get when you plug 2 in. It's negative 1. So your answer would be yes. And go ahead and write that formal definition. As we approach 2 from the left and the right of f, it equals f of 2. That was, right, the first definition of continuity that I wrote over here on the board. It is continuous because that is true.
Did you just write 2 instead of 2? The bottom might be yes, and the next is
Jack, what do you think? Annabelle, what do you think?
So instead of saying
Great.
2 9 you can just say
Good.
yeah.
All right, let's change up the directions here real fast. Emily, you like when the directions change? Good.
Do one that includes 4 times 8. Well, it's not. So important.
Identify. All right, so here we go. Identify any points of discontinuity. Right? And classify them as removable or non-removable. All right, I'll let you copy that down for a second. Molly, you ready? All right, Molly, let's do it. What's this example number? What was this?
3.
3. All right, cool. This will be a 3-parter, Molly.
Okay.
You don't have to do all 3 parts.
Thank you.
I'll pick on 12 here in just a minute. I mean, that was a joke. I mean, it just went over everybody's head. It's fine.
That was really they don't get the inside joke. No,
Okay,
it's
that's
fine.
fine.
I think you need to announce it. No, it's actually okay.
All right, Molly, here we go. Identify any points of discontinuity. Where does this graph have some kind of hole, jump, gap, asymptote, whatever. So when you look at that, what kind of draws your attention if you're looking for a place where it's not continuous?
The
What do we call that on the, what do we call that on the bottom?
vertical asymptote.
It's a vertical asymptote, right? We know the vertical asymptote right here is x equals 1. And you're like, holy cow, Mr. Baker, I can draw a graph over here. I got 1 over here, it's a vertical asymptote. I got a horizontal asymptote here, 0. Okay? We've been drawing graphs like that for a hot minute, right? So if you have that in mind, obviously, right, I am discontinuous, right, at x equals 1. But now we have to classify it. We have to classify that. Well, here's how it works. Removable means you can still find the limit at that value, right? Removable means you can still find the limit at that value. Non-removable,
You can't find
you can't find the limit. You got that?
Mhm.
So, Molly, here's what I'm saying. If I wanted to find the limit at 1, I'm coming here from the left, negative infinity. I'm coming in here from the right, positive infinity. Can I find the limit?
Yes.
Did the limit equal each other from the left and the right?
Yes.
No.
No.
One's negative infinity,
Oh, no.
one's positive infinity. So does the limit exist? No, because we're approaching different values. So if you can't find the limit, what do we call it?
Non-removable.
That's non-removable. Okay? It is non-removable. So Andrew, what does continuous mean in your brain?
The limit from the left and the right are equal to the.
Function value. And Andrew, if you ever see these phrases, you got to, I mean, it's just, I know it's a big, long ear.
Yeah.
You know what I mean? Like when you see non-removable, you got to be like, wait a second, non-removable means I can't find the limit. Removable means you can. Okay? Cool with that? Carter, you got that? Carter, 99.999% of the time, vertical asymptotes are always
Non-removable.
non-removable. Okay? Just throwing that out there. All right, part B right here real fast. We can do this one. Emily, identify all points of discontinuity and classify them.
No.
So what comes to mind, Emily? What do you want to do?
The vertical asymptote.
Well, you would only do vertical asymptotes after you factor and simplify, right? So, okay, so real quick, what do we call that on top?
Difference of squares.
Difference of squares, how do you factor it?
Oh, that's plus 1, that's minus 1.
Making her proud. That's good. Emily, what cancels out?
That's minus 1.
Okay, so Emily, where am I discontinuous?
1.
You're discontinuous at x equals 1. What is technically 1 actually? It's a whole, right? I'll just put that in parentheses. You know, it's in your brain. You are discontinuous at 1 because it is a whole. Real fast, real quick right here. Emily, when I simplify this, really I'm just left with a line. You know what I mean? That's a line. That's like y-intercept of 1, slope is up 1, right 1. But technically when you hit 1, you have a whole, right? If you plug this in your calculator, this function, will your calculator show you the whole at 1? No, that's why it's always good to be, you're smarter than your calculator. Okay? You are, Emily. You are smarter than your calculator. So Emily, what is 1? Is it removable or non-removable? Let me ask you this. As I come in from the left on 1, my limit is 2. As I come in from the right on 1, my limit is also 2. So what kind of discontinuity is this? It's removable. Why, Emily? You can still find the limit. Carter, 99.999% of the time, holes are always what?
Removable.
Removable. As long as you can find the limit though. Okay, most of the time. I'd say just most of the time. Good, good. Anashka, you good? Can you take a picture or anything?
No. I'll take it in my mind.
Okay. Yeah. Probably just at your desk at home, you know, next to your other stuff. So it's good. Good. All right. Part C. Carter, you want this one?
Let's do it.
All right, Carter. I'm I'm just waiting to call on Jack at the right
I'm
point.
tired, like, it's different. No, it's just, it feels weird.
Jack, don't worry, I'm gonna get you in today.
It feels weird when you do it, it feels like on opposite side.
No, Jack.
Well, if it feels.
I feel empty inside if we don't have our calculus conversations. Jack. Okay? Alright, Carter. I wanna know if this function has any points of discontinuity. So, train of thought right here. This is a piecewise function. What kind of a graph is that, Carter? What's x squared plus 2?
Parabola.
It is a parabola. Do parabolas have any holes, jumps, gaps, anything, or are parabolas continuous?
They're continuous.
Yeah, exactly. What kind of graph is that?
The linear.
Regular old line. You know what I mean? Do lines have any holes, jumps, or gaps?
No.
No. So, Carter, where could I have a possible point of discontinuity? If that thing is continuous and this is continuous, where could this possibly have discontinuity?
Where
What
it
do you-
intersects. Or nowhere. One.
At x equals 1. Right? At x equals 1. Which basically kind of means I need to check the left and the right to make sure they equal each other. Right? Which also equals the function value, Andrew.
Yeah.
Which, what is that definition again?
Continuity.
Continuity. You know what I'm saying, Carter?
Yeah.
So Carter, real quick here. If I approached 1 from the left, is that the top function?
Yes.
Yeah, I get 3. If I check the limit from the left on 1, I'm sorry, left is there, 3. If I check it on the right of 1, you'd have 5x minus 2, which is also 3. Should you verify that f of 1, Carter, is also 3?
Yes.
Which in this case it is, right? The left and the right equal each other. When I plug 1 in up here, you'd use that top one because you're less than or equal to 1. And you also get 3. So, are there any points of discontinuity on this graph? No, Carter. I mean, honestly, Carter, I mean, this is like going way back right here. You ready for this?
I'm ready.
What's the vertex of that parabola?
0,
0, 2.
2.
Good, Carter. You remember that?
No.
All right. Carter, what's this?
Vertex.
Form of a yeah. Carter, you know what I'm saying? Carter, was there anything in there with x?
Yeah.
No.
No.
You don't see any parentheses up here.
Oh,
You know what I'm saying?
oh, yeah.
Is there anything in there with x?
No.
No, so it's an automatic 0. Was k 2?
Yes.
So Carter, what's the vertex of this parabola?
2. 0, 2.
0, 2.
2.
Right? So like that's why I could like come up here and be like, oh, 0, 2, there's my vertex. Right? You actually know parabolas do this, and it just so happens that it hits right here at 1, 3. Right? It does. I promise you. Don't worry about that. Carter, is that a line?
Yes.
What's the y-intercept?
2.
Good. Carter, just breathe. Okay, I think the pressure's getting to you. Carter, what's this?
Oh, okay. -2.
I didn't ask that. What's that?
It's a slope form to the formula.
Carter. All the math comes together. So Carter, say it one more time. What's that? You were close. Just
Slope intercepts form.
slope intercept. Do we do that a lot in calculus?
I bet. Yeah.
Absolutely, we will. Oh man, when we start talking about derivatives, you and this formula right here, Carter, can become best friends. Okay?
All
So
right.
Carter, y-intercept is -2, right?
Yes.
Technically, you'd start down here. Your slope is 5. So you would go up 5, like 1, 2, 3, 4, 5 over 1, right? And technically, you would have this line, Carter, but I'm not gonna really graph it till I get to the right of 1, right? You know what I'm saying? So when I graph this, it actually looks like that. honestly, right? When I look at the graph, there's no holes, jumps, or gaps there. That function is actually continuous. Everywhere. You got that, Carter?
I got it.
Thank you. Jack, you ready?
Yeah.
All right, Jack. Jack, what number is this example?
4.
4, let's do it.
Jack is so happy.
Hey, Carter, what's this?
Slope.
Stop it. What's that?
Point slope, sorry.
Point slope. Okay, good. What's this?
Just slope formula.
Good. Carter, what's this?
Is it the distance?
Is that a question or a statement?
It's the distance.
Yeah, it
formula.
is. That's good, Carter. Carter, do we use all this stuff in calculus?
Yeah, I bet.
Yeah? What about this, Carter?
Haskell's triangle.
Yeah, do we use that in calculus?
Yes.
Yeah, we do. Good time. Sorry, Carter, I just got excited. Mr. Baker likes math.
I bet.
Jack, you ready? All right, Jack, here we go. Jack, if you want to know what a AP multiple choice question looks like, and they put this on the exam, if they like it on the exam, do you think it might show up on your test?
Yeah.
Okay, good. So here we go. Find the value, could be values, of K that make the function continuous. There's your favorite word, Andrew. Okay. All right, Jack, just to make sure you've been paying attention, because I know you're an excellent pay attentioner. Okay? Jack, what does continuous mean again?
The limit from the left equals the limit from the right, and the function value. at
Excellent.
C.
Excellent. Thank you. I feel accomplished today. Thank you, Jack.
Yeah, that's fine.
All right, so Jack, that's what's going to happen. Jack, from here, I mean, the whole year, students always ask Mr. Baker calculus questions. Like, Mr. Baker, I don't know what I'm doing. I'm stuck. I always ask the exact same question back to you, honestly. And 99% of the time, it's, what do you think the buzzword is in the question? You know what I mean?
Is that a question for you?
No.
Okay.
But now it can be. What is the buzzword in this question?
Continuous.
Continuous, right? If you ever get stuck in a problem, I'm going to look at you and be like, what's the buzzword? And you can be like, maximum. And I'd be like, exactly. What does the maximum tell you about derivatives? You know what I mean? Like all this stuff. You know, but we're not there yet. We're just talking about continuous. You know what I mean? So, you just said it. The left should equal the right, which also should equal that function value. But they told you in the problem, the function is going to be continuous. So you therefore really just need to say the limit from the left and the limit from the right need to equal each other. So what do you think I'm about to do right now? It's not, you're going to set them equal to each other and plug in what?
3.
You're going to plug in 3. You would literally do 2 times 3 plus 9 equals negative 4 times 3 plus k. You get 6 plus 9, you get 15, right? You get negative 12. You add it over, and k is 27. You circle that on the multiple choice, and you're like, I got that point right there. Life is good. You know what I'm saying?
Yes.
Right.
No.
Slope intercept form, Carter. Go team.